Okay, now we'll look at question 3. In question 3, the focus will be on the strength of ionic bonds. Okay, so just now we look at covalent bonds. Now we'll look at ionic bonds. Okay, so the strength of ionic bonds is given by something called the lattice energy. Okay, so in this question, you are given experimental data of lattice energy. Now, experimental means that an experiment was carried out to determine the value of the lattice energy. So it's really the actual value, okay, the real value, as opposed to theoretical value. Okay, theoretical means that we use some formula to calculate the expected value for the lattice energy. Okay, but it may not be the real value. So it's something like you use the ideal gas equation to calculate the expected value for a gas. Okay, but it may not be the value that the gas exhibits in reality. Okay, so here for every compound, you are given two sets of value, experimental and theoretical. Okay, so notice that these values are negative. So in other words, lattice energy is exothermic. Okay, why is that so? It is simply because it is simply related to how lattice energy is defined. Okay, so for example, if we look at lattice energy of sodium chloride, this is the definition. Okay, so it's the gaseous ions coming together to form 1 mole of the solid compound, right? So basically this process involves formation of ionic bonds. Okay, so it's not breaking of the ionic bonds. So that's why lattice energy is negative. Okay, but here we'll just look at the magnitude of the value to determine the strength of the ionic bond. So for part A, draw a dot and cross diagram for sodium iodide. This one I think you should be able to manage on your own. Right, so I just show you the answer, sodium iodide. So make sure you use different symbol, right, to differentiate the electrons of iodine itself and this electron which is gained from the sodium atom. Okay, part B is what I'm interested in. So why is the lattice energy of sodium iodide less exothermic than that of sodium chloride? So if you just look at the value, it simply means that the ionic bond in sodium iodide is weaker than sodium chloride. Okay, so you have to look at the factors that affect the strength of ionic bonds. So simply put, there are two factors, charge and size. Okay, so I think it's quite obvious. The higher the charge, the stronger the ionic bond. Okay, because the attraction between the ions will be stronger. Okay, the larger the size, the weaker the ionic bond, and hence the lower the lattice energy. Okay, because when the ions are big, that means they are further apart, and therefore they attract one another less strongly. So to explain the difference between sodium iodide and sodium chloride, you have to look at the charge. So the charge is the same for both compounds, okay, but the iodide ion is larger than the chloride ion. Okay, so that's why the ionic bonds of sodium iodide is weaker. The lattice energy is also smaller. Then here I also want you to be careful in the terminology. So for lattice energy, we are dealing with ionic compounds. So you should be using the term ionic radius, not atomic radius. Okay, whereas in the previous question, when we were dealing with bond energy, that's for covalent molecules, which consists of atoms. Okay, so for bond energy, we use the term atomic radius. Okay, for part C, what we are going to look at is something called polarization. Okay, so you are told that silver fluoride and silver iodide, they have the same crystal structure. Okay, but there's close agreement between the experimental and theoretical values of the lattice energy for silver fluoride, but not for silver iodide. So suggest a reason for this. So let's look at the data again. Okay, so you can see for yourself that for silver fluoride, there's very good agreement between the two sets of values. But for silver iodide, the difference is larger. Okay, so for this one, you need to understand that the theoretical values actually assume that the compound is purely ionic. Okay, but now at A level, you must be used to the fact that compounds need not be purely ionic or purely covalent. Okay, the bond, okay, can have a mixture of ionic and covalent character. So based on this, based on the data, okay, which compound has more covalent character? The answer is silver iodide, right? So it's because silver iodide has more covalent character, so that's why the theoretical value doesn't agree very well with the experimental value. So why does silver iodide has covalent character? This is related to a phenomenon that is called polarization. Okay, now we start from this basis that the compound is purely ionic. So in a purely ionic compound, right, the cation and the anion will have its own separate electron cloud. Okay, now polarization simply means that the cation attracts the electrons of the anion towards itself. And as a result, can you see that the electron cloud of the anion is distorted? Right, some of the electrons is attracted towards the cation like this. Okay, so the term that we use to describe this is that the silver ion, the cation, distorts or polarizes the electron cloud of the anion. Okay, I repeat, in polarization is the cation that attracts or polarizes the electron cloud of the anion towards itself. So as a result, the electron cloud of the anion is distorted. Some of the electrons are attracted towards the cation. And as a result, can you see that these electrons now, they don't belong solely to iodide. Okay, they are also they are also like partially owned by the cation. Okay, so as a result, there's sharing of electrons. So whenever there's sharing of electrons, that means the compound has higher covalent character. Okay, because covalent bonds is formed from sharing of electrons. Okay, so once there's some sharing of electrons, the compound will have covalent character. So I also want you to take note that it's the cation that is polarizing or distorting the anion, not the other way around. Okay, so the anion cannot polarize. It's the cation that polarizes. Okay, so the extent to which polarization takes place depends on two factors. So if you look at a cation with high charge density will be strongly polarizing. Charge density is defined in this way, charge over size. Okay, I think there's a mistake in the notes that I sent out to you. Please change the mass to size. Okay, so charge density is charge over size. Size meaning volume or radius, not mass. Okay, so basically charge density, right, tells you how concentrated the charge is. So for example, you can have two cations with the same charge. Okay, but the cation that is smaller will have more concentrated charge. the charge is actually more concentrated in the smaller cation. So we say that it has a higher charge density. Okay, so obviously a cation with a charge that's more concentrated can attract the electrons of the anion more strongly. So as a result, it's more strongly polarizing. Okay, then now we look at the anion factor. Okay, so an anion with high charge will also be easily polarized or easily distorted. Quite obvious this one, right? Because when the charge of the anion is high, that means the attraction between the cation and the anion will be strong. So that will aid the distortion. Okay, then here this one is different from cation. So for cation, we say that it must have a high charge density to be strongly polarizing. So one way to have high charge density is to have a small cationic size. Okay, but for anion, it's not small size, it's large size anion that will be easily polarized. Okay, the thing is this, if the anion is large, that means the distance between the outermost electron and the nucleus will be greater. Right, so as a result, the outermost electron is more weakly held by the nucleus. Okay, and therefore this anion will have a weaker control over the outermost electrons. So as a result, the outermost electrons are easily attracted towards the cation. Okay, they are easily attracted by the cation. So that means the anion is easily polarized. Okay, so for part C, the answer why silver iodide has more covalent character is related to the anionic size. Okay, so it's because iodide is bigger than fluoride and therefore is polarized to a greater extent. So silver iodide will have more covalent character. Okay, so this is the end of question 4.